All right, chapter 1, part 2, looking back in time. So light travels at the finite speed of 300,000 kilometers per second. Um, this number is huge. Nothing can reach to this number. Nothing can reach to this velocity. If a physical matter reaches to this velocity, it will be destroyed. It will be completely turned to energy. So you cannot accelerate anything to this velocity. If anything that has a physical appearance reaches to this velocity, it will be completely turned to photons, to energy. Okay, so this if you travel with this speed, let's say, or when the light travels with this speed, in order to get to moon, it will only require 1 second. So 1 second later, it will reach the moon. It will take about 8 minutes for the light to travel between Earth and Sun. So the the sunlight that gets to us now, it was emitted from the sun 8 minutes ago because it took it 8 minutes to get to us. So as you're looking at the sun right now, if you're watching this video during the day, if you're looking at the sun right now, you're looking at it as it was 8 minutes ago. Ceres, 8 years. It will take 8 years. So if you're looking at the Ceres, it's another star. It's a very bright star at night. If you're looking at it tonight, you're looking at Ceres as it was 8 years ago, because it's taking 8 years for the light to get to us. And for example, Andromeda Galaxy, it is taking the light 2.5 million years to get to us. So if you go out and you set up your telescope at night and observe Andromeda Galaxy and successfully observing it, you're looking at it as it was 2.5 million years ago, because it took it 2.5, it took the light 2.5 million years to get to us. Therefore, we see objects as they were in the past. If for whatever reason Andromeda Galaxy completely disappeared today, we wouldn't even know until 2.5 million years from now, because we're constantly getting light and we're constantly looking at the past. The further away you look in distance, the further back we look in time. So let's take a look at an example. This photo shows the Andromeda Galaxy as it looked about 2.5 million years ago. Question: when we will see, or we will be able to see, what it looks like now? In other words, if I want to see this galaxy now, I have to wait 2.5 million years for its light to get to me, and then I will be able to see it today, because it is taking time for the light to travel. So with that concept in mind, let's now talk about light year. The distance that light travels in 1 year. In other words, let's say that somebody is setting up the time and counting for 1 year, and somebody is measuring the distance that light can travel in that 1 year time period. That distance is called light year. Remember, the light year is not a unit of time. It is a unit of distance. If we are saying that the distance between Alpha Centauri and our sun is 4 light years, it means it is taking light 4 years to travel between these 2 points. It is a distance, a unit of distance. It's not a unit of time. So it's about 10 trillion kilometers, or 6 trillion miles. Okay. At great distances, we see objects as they were when the universe was much younger. So if I am looking at 7 billion, a light at 7 billion years, we see a galaxy 7 billion light years away as it was 7 billion years ago, when the universe was about half of its current age. The current age of the universe is about 13.8 billion years. If you are looking at a light that is 12 billion years, for example, we see a galaxy that's 12 billion light years away. We are looking as it was 12 billion years ago, when the universe was much younger. It was only 2 billion years old at the time. And 14 billion light years, this is the limit of our observable universe. Light um, from nearly 14 billion light years away showed that the universe as it was shortly after Big Bang. Okay, beyond that we cannot really see anything because um, beyond 14 billion years, because its light has not had enough time yet to reach to us. Okay, um, so we don't really know. Uh, all the information that we have is about 14 billion light years away. A thought question for all of you that watching this. Normally in class, I usually wait for students to answer, but think about this question for a minute or so, and I'll just show you the answer. I'll talk about it. I'm going to read it. Why can't we see a galaxy 15 billion years away? And this is with an assumption of the universe being 14 billion years old. So take a look at this question, read A, B, or C, and uh, see what you think. A is no galaxies exist at such a great distance. B is galaxies may exist at the distance, but their light would be too faint for telescopes to see. And C is looking 15 billion light years away means looking at a time before the universe existed. And as you said, I'm pretty sure most of you said, looking 15 billion light years away means looking at a time before the universe exists, and we simply can't do that. So, how big is the universe? How big is it? Let's take a look. Let's reduce the size of a solar system. Our solar system, that means um, the 8 planets, the 8 official planets that we have and our sun. Let's reduce the size of it by a factor of 10 billion. Okay. The sun, if you do that, if you reduce the size of the universe 10 billion times, the sun is now the size of a grapefruit. So when you go to a grocery store to do some fruit shopping or to do some grocery shopping, take a look at a grapefruit, a large grapefruit. If you reduce the size of the sun 10 billion times, you'll end up to be in the size of a grapefruit. Now the question is, if we do that, how big is the earth in that scale? How big the earth would be if we reduce the size of the earth 10 billion times? The answer is it would be the tip of a ballpoint pen. Very, very small. Okay. Now, um, I will show a little video or a little animation, and they are available on Canvas for you. So um, that you can play with them. So this is basically 1 to 10 billion scale. Okay. So let's do that. So this is the National Mall in Washington, D.C., National Air and Space Museum as well. Now, if I start to zoom out from Washington, D.C., and let's say that everything, the grapefruit that we were talking about, the sun that is now 10 billion times smaller, let's say that we want to put that in Washington, D.C., okay? Right here. This is where we put the sun. if if we reduce the size of everything in the universe 10 billion times, then our Earth is right here about 15 meters away, about 15 yards away. Mars is about 23 yards away. Jupiter is 78 meters or 78 yards away. Saturn, Uranus, and Neptune, as they are indicated in this picture. So this is with the assumption of everything being 10 billion times smaller. Okay, now let's zoom out a bit. Okay, now where do you think the next star would be? Remember, everything is shrinked. Everything has been, the size of everything has been reduced 10 billion times. And this is where the grapefruit or the sun is. Where do you think in this map the next star would be? Would it be somewhere in the middle? Somewhere up north here? Where would it be? The answer is it would be in San Francisco. This is the closest star, Alpha Centauri, which is about 4 light years away from us. So if you reduce the size of everything in the universe 10 billion times, the next star from the sun would have this distance, the distance from Washington, D.C. to San Francisco, approximately, not exactly, approximately, which is about 2,600 miles or 4,200 kilometers metric system. Okay, zoom out a little bit more so you kind of know what I'm talking about. So if this is with the consideration, if everything is 10 billion times smaller, then the sun and the next star would have this much distance, 2,600 miles. Okay, now with the same concept, I wanted to zoom out a little bit. Remember, this concept is that everything is being decreased, the size of everything being decreased 10 billion times. I wanted to zoom out a little bit more. So this is the sun and Alpha Centauri from Washington, D.C. to San Francisco. And I'm zooming out. In that scale, I'm still zooming out. I want to know what would happen to Milky Way if the size of a Milky Way reduced 10 billion times. What would it look like? It would fit between the Earth orbit and the sun. So if you can somehow reduce the size of Milky Way 10 billion times, it would fit between sun and Earth, the real sun and Earth distance. So it will be this much. Okay. All right. So this is what I was talking about at the beginning of chapter or our address. So this is our universe or observable universe. And then if you zoom in, that would be their local supercluster. It's a supercluster is clusters of galaxies. So you can see hundreds of them. And then that is our local group. This is our Milky Way. This is the Andromeda Galaxy, which takes about 2.5 million years for its light to get to us. This is our Milky Way. I'm just zooming in a little bit more. And sun location is in a great location. It's not really that close. It's not really far away. It's in the perfect standard, perfect great position. And so that's the position of the sun. There are millions of the stars. That's Polaris, which is always pointing, our North Pole is always pointing towards this star. In other words, this star is not really moving around much in our night sky. That's our sun. and that's star Betelgeuse, is one of the brightest stars in the sky night. Star Vega, Ceres, and that's our sun. That's Alpha Centauri, which is 4 light years away. Remember, we were able, if you reduce the size of everything 10 billion times, Sun and Alpha Centauri, they will have the distance between Washington, D.C. and San Francisco. But in reality, they're 4 light years away. That's our sun. I'm just going to zoom in a little bit more. Orbit of Pluto and Neptune, uh, giant planets zooming in, and that's the orbit of Earth, orbit of Moon, and I'm just going to zoom in a little bit more. The funny thing about this that every time that I play this, I feel super small and not very important at all. In terms of um, our cosmic address in the universe, we are nothing. Okay, because we are just a point in the galaxy, and that galaxy is um, one of the billions of galaxies that exist in the universe. So, you know, I feel really small every time that I play this. Well, let's go back to our PowerPoints. I just played that. Now, um, on our 1 to 10 billion scale, it's just a few minutes to walk to Pluto. How far would you have to walk to reach to Alpha Centauri? The answer is right here. The distance across the United States, about 2,500 miles. So the answer is D. We just played that. The Milky Way has about 100 billion stars. Okay, and if you play this, it would fit if you kind of reduce the size of it to 10 billion degrees or 10 billion times smaller, you can fit it between Earth and Sun. So a thought question now. Again, you can pause the video right now and read this thought question, think about the answers, and I'll talk about it. So suppose you tried to count um, more than 100 billion stars in our galaxy at a rate of 1 per second. So you are counting counting them, but you're counting 1 per second, and you're not recounting. Okay, so you kind of remember what you've already counted. How long would it take you to count everything? Few weeks, few months, few years, few thousand years. It'll be few thousands. So with the rate of you are counting one galaxy per second, it will take you few thousand years. And when I'm talking about few, it's about 3,000 years to count them, to count all of them. Okay? That's how many we have in the universe. So the Milky Way, which is our galaxy, is one of the 100 billion galaxies that are out there. And each galaxy has about 10 to the power of 11 stars. So one galaxy has 10 to the power of 11 stars. How many galaxies we have? 10 to the power of 11 galaxies. And that means we have 10 to the power of 22 stars in the universe. That means there are so many stars that the number of stars is more than the number of dry sands in the earth beaches all combined. So in other words, put 1 and 22 zeros in front of it. I can't even, I can't, I have a hard time understanding that number. 22 zeros in front of this 1. That's the number of stars in the universe. And our sun in our solar system is only one of them. That's amazing. So we just zoom out. I just show you that little animation, and they are available. You can try, you can play with them. But every time, as I said, every time that I play that, I feel like super small. So let's see what I've learned. So Earth is part of the solar system, which is the Milky Way galaxy, and which is in the Milky Way galaxy, and which is a member of the local group of galaxies in a local supercluster. And the observable universe, uh, in the observable universe, um, we don't we know that observable universe reaches about 14 billion light years away, or 14 billion years old, in fact. But we don't really know behind it. We don't really know what happened at the time of the Big Bang. The time of the Big Bang is the initial time that created, um, kind of validate or kind of introduce the time test. We don't really know. We can think about it mathematically, but we don't really know what is behind it. What's before that. And the concept, the human concept, cannot understand the negative time, or we don't really know what happened or what caused the Big Bang, or at least we cannot, with science, um, prove or understand what's happening behind or what's happening before the Big Bang. So this will be the end of part 2 of chapter 1. I will go ahead and start recording part 3. Stay tuned, okay?